Have you ever thought about evolution of RC toys? Flying drones and FPV technology made a huge jump in the last 20 years, and today everyone has an option, no matter the budget and skill. There are a lot of cheap Chinese toys for kids. Plug-and-play Whoops or DJI drones for people who have money and want to film cinematic shots with easy control. But the best part is that there are a lot of hardware and software to build your own custom drone, no matter the size or purpose. With Betafly, you get a beginner-friendly configurator where you can add motors, servos, LEDs and sensors. With ArduPilot, you are limited only by laws of physics. You can build autonomous drones that fly pre-planned missions or even use computer vision. But what about cars? Personally, I feel a huge gap in possibilities to create custom builds. And I'm not talking about frames or custom bodies, I'm talking about features and flexibility to configure them. For example, I bought a $30 controller and receiver. The only control I get is 4 PWM outputs, and 2 of them are already reserved for motor and steering. To connect LEDs, which cost almost nothing, I need a $7 module. To connect a gyro, which also costs almost nothing, I need another expensive module. If I want precise control of one more servo, I had to buy a new controller and a receiver just to get more PWM outputs. And it really upset me that the only way to build something more advanced is to spend days writing custom firmware for a microcontroller. Lastly, one more thing. I hate RC car controllers. I think a lot of people would agree with me that using a quad controller, PS5 DualShock, an Xbox controller, or even a real wheel would be much better. So I've spent 2 months of my life writing MVP for my system which should fix all these pain points. The Betawrite concept is similar to FPV software. After uploading the firmware to ESP, you'll get access to configurator. Just plug in USB cable and connect the device. Now you can add the resources you plan to use in your build. For now, they are limited by motors, servos and ELRS controller. The system will automatically assign GPIO pins, helps you with the PWM settings and establish communication with the controller. Then you can define how the resources should behave based on your controller output. Before I show you a more complex example and explain in details how software works, I want to ask you a favor. This project won't survive without an audience. I can't properly test all use cases, I have limited vision of hardware should be used, and I definitely can't move forward without feedback. So, if you're interested in building custom robotics, I've created a Discord channel. There you can propose features, report bugs, give feedback, ask questions or share your creations with others. All links in the description. To show the main idea of the software and give you some tutorial, let's connect and configure ELRS, one brushless motor, one N20 motor, a few servos. The brushless motor will be controlled by throttle. Changing the AUX position will make it spin in reverse. This servo is for main steering. When the switch is moved to upper position, we enter a different mode. Now, YAV will control N20 motor, while pitch and roll will control other servos. First, we need to upload the firmware. You can either clone a Git repository or download the latest release as a zip archive. Then, open it in VS Code with Platform IO installed. Next, plug in the USB cable, build and upload the firmware. You can do it manually using the commands from README file or directly through the VS Code interface. Currently, the firmware has only been tested with the ESP32 dev board. Other boards may have different timer configs and PWM pins, so you might face unexpected issues. To verify that the firmware uploaded, check the serial monitor. Depending on the debug build flag in the config file, you'll see slightly different output. Then navigate the configurator page. Select the USB port and press connect. Since configurator uses the same serial monitor, you'll receive the error if forgot to close it in VS Code. We start from the resources page. First, let's add a controller. Right now, only ELRS supported, but in the next update I'll add a PS5 DualShock controller support. Next, I'm adding a brushless motor. To make resources easier to identify, I'm giving them meaningful names. At this stage, resources are created with predefined configs, which can be changed later. Then, I'm adding the N20 motor and servos. Currently, there is a limit for one controller and up to 10 resources of each type. However, you won't be able to add more resources if all pins or PWM channels are already reserved. Once all resources are added, I hit the Save button. This step isn't necessary because the configurator keeps your state when switching tabs. You won't lose data before disconnecting. But by saving the resources now, I enable the controller connection. After plugging in the wires, I can already see output and stick reaction in the controller section. But first, let's configure the motors. In most cases, an ESP can't control a motor without an additional driver. For DC motors, I've chosen DVR8833 driver. There is no limitation on driver choice, as long as it has two PWM inputs for bidirectional control. When we send a PWM signal to the first pin and keep the second low, the motor spins forward. To reverse direction, we send a PWM signal to the second pin and keep first low. With that in mind, I'm adding the second pin. Now we enter the only tricky part of the whole software. I've tried to simplify it as much as possible, but it's very important to understand some basics, so I should briefly explain some boring theory. To generate PWM signal, ESP use timers. The crucial rule for correct operation is all channels on the same timer must use the same frequency. To manage this mess, I've added a small visual map of timers and channels. So if I try to assign a 50 kHz motor to a timer already running 50 Hz servo, you'll see an error message and a visual hint showing that something wrong. You can bypass this protection and save the config anyway, but only do it if you absolutely understand why you need it. Okay, let's get back to our motor. PWM frequency is usually described in the driver's datasheet. For most of them, it's in a 10-50 kHz range, but you can experiment with it, nothing critical shouldn't happen. The resolution defines control precision. 8-bit means the motor can react up to 255 different PWM values. 16-bit gives you over 65,000 steps. The natural instinct is to always use the highest resolution possible, but there is a limitation. The ESP can't handle high frequency and high resolution at the same time. It's limited by a clock speed. So, if you see such warnings, just lower the resolution or frequency. And lastly, I've added a timeout to prevent instant switching between motor direction. I bet nothing good will happen if you enable reverse mode at a full speed. Brushless motor configuration is very similar. Currently, the software controls the brushless USCs with BLHeli-S firmware. The signal wire should be connected to the GPIO you selected. PWM configuration follows the same logic I described earlier. The only difference is the values in microseconds and 3D mode, which you should get from your ESC configurator. And lastly, servos. The same PWM configuration principle applies. Min and max pulses depends on a specific servo, but in most cases you can leave them as default. You need to specify the max angle for your servo, and this is important for proper control. The center angle is used as a default position and could be used for fine-tuning instead of controller trims. And finally, I can link controller outputs to other electronics. To do this, I've created a simple rules engine. When a controller output meets a condition, the effect applies to the selected resource. In our example, the throttle channel can be fully mapped to a brushless motor. The same percent throttle gives the same motor speed. If we want the same channel to control multiple effects, we need to add a subcondition. In my case, I want this effect to apply only when AUX3 in the lower position. Now I'm adding a similar rule, but with AUX3 in middle position and changing the effect to backward direction. If you feel that full speed isn't needed, instead of mapping 0 to 100%, you can remap the stick range to, for example, 30% maximum speed. This is also helpful when you want to eliminate motors that bend. A similar approach applies to servos. I map the whole roll channel to the full servo rotation. The only difference in the subcondition. The servo should be controlled all the time until AUX3 is in bottom or middle position. Now let's map the other two servos to roll and pitch when AUX3 in top position. To control a motor in both directions with one stick, I change the full map in one condition to a specific range. If you ever configured DC motors, you know that they have a dead zone that depends on a specific motor and its load. So I'm mapping speed starting not from 0, but from 50%. And that's it. Without filming the video or adding explanation, the whole configuration takes less than 5 minutes. Once you get the idea, you can build complex system without diving into technical details. Since you watched till the end, I bet you're interested in trying Betterwrite yourself. Whenever you need some help, jump into Discord and feel free to ask any questions, propose changes or suggest improvements.